Well, hello everyone. Can you hear me well? Thank you, Yana, for the introduction. And well, let's start with the webinar. So we come from a series of three in total. We have had first Sasha Krause-Tunka with an introduction to the concept, to the vertical bifacial system. Then we had the second one with Peta Bendix about the yield simulation and more technical topics about vertical bifacial. And today the idea is to integrate both topics, viewing some examples, concrete business cases, and case studies of projects that have been already built, so that you can have a better idea and a more concrete idea, and also try to find new applications for the system. So we are going to see two cases with more depth. The first one is a case study about a 4 megawatt project we have developed and built here in Germany, in Baden-Württemberg. This project is about to go online the next days, we hope. And the second one is a business case about the synergy that can be achieved between a south-oriented fixed plant and a vertical bifacial plant with our system. And then we're going to see less in depth, some other business cases and case studies that are interesting about Agri-PV and other applications with our solar fence. So if you missed the previous webinars, don't worry about it. You can watch them on Vimeo on our channel. So this is also going to be uploaded, so you can watch them whenever you want. Well, we start with the quick facts about our 4 megawatt project. It was actually the third one that we have built. The first one was a pilot project, a minor pilot project to see how the performance and everything else went with the system. This was very successful, so we built a second one. This was a 2 megawatt project in Saarland, and this is the third one. So the location, as we already said, is in Donaueschingen. This is in the south of Germany. The size of the field is 14 hectares, and we have used 5,700 bifacial modules. The energy output is 4.1 megawatt peaks. We have an annual energy output of 4,600 megawatt hours per year. The panels are facing east and west, so the faces are facing in these directions. And well, this is the biggest plant in Europe with this system so far, so we are proud of it. You can watch a video we have uploaded on LinkedIn with this link once you get to download this presentation. Well, the field is between two highways, and well, we have built there 33 rows of panels, and the spacing is of 11 meters between the rows. So let's see a little bit more in depth what happens between the rows. So here we have a very simple diagram about the distance between the rows. So in the middle, it is possible to do a lot of agricultural utilizations like meadows, arable land, and other kind of activities. Also, livestock farming is possible. We have tested it, so it's compatible. And under the rows, you have strips of grass that are about a meter of width. So this is basically how it looks like. And well, this aspect, the key aspect in this project was the good acceptance that we had with the landowners, the farmers, and the authorities. And the most important thing that allowed us to be successful here was the permitting process. So with our system, the water supply remains almost unchanged. The changes in insulation are very low as well. They are between 10 and 15%. So as well, it has a very insignificant level of overbuilding. So less of 5% of the ground surface is occupied by our system. And in addition, once the project lifetime has finished, the system can be put out with no major work, because the profiles are rammed in the ground, and so you don't need to have any concrete building and things like this. So it is very it is not intrusive for the land. Also, the appearance is different, so it looks more it is not that invasive by the appearance, and you don't have dazzle effects that can be a problem when you build in fact next to highways or streets. So in this particular project, 2 hectares of the land have been converted from arable crop to grasslands. The rest was already grassland. The rows were adapted to the machines that were used. So every project has to be thought or designed in base of what activity is going to be held in between of the panels. The machines do need to work a bit slower, so it's about a 30% lower, but this is possible to be improved with GPS systems or Internet of Things applications or other technologies. Plus is that the erosion in the field is less, because the wind speed is lower with our system. And in comparison with other Agri-PV systems, our system doesn't generate drops that go to the crop. All drops get to the grass strips, so this is not a problem for the agriculture activity. And also, in this particular project, there is no need to clean the panel, so the rain does all the work. Of course, this may vary in other areas. Here in Germany, we have pretty much rain, so in other areas this might be necessary. I mean, but in any case, it will be less than other fixed systems or with systems with trackers as well. So getting a bit more in depth with the system, with the mounting system itself, we see that it is very modular. It is done. It consists of ramming profiles that are rammed into the ground. Then they have piles that are screwed to the ramming profiles. So this is very convenient when it comes to be precise on the ramming. You can absorb any misalignments of the ramming process, and also it is designed in a way that it allows to have as far as 20% of slope. So if you have a terrain that is not even, it is very permissive in this case. So also, well, it is designed to be very efficient in building, and it is fast to be built. And well, for the placement of the inverters, we have inverters. We leave one spot free of panels, and we install the inverters. And well, once we have said so, I wanted to share with you some important an overview of the financial numbers, so you can analyze your own projects, or you can have an idea how this works. So for doing so, I want to compare what would have happened if we build a south-oriented fixed monofacial system instead of our system with exact the same power. So you can see how it looks like in comparison to a fixed system. So the specific yearly energy production in this case was a bit higher than the south-oriented system. For knowing about the performance, we have, of course, you could see it in the second webinar that Peter told about the simulation and so on. So in this case, we had a slightly higher energy yield. The degradation in the technology that we used, the panel technology that we used, is a little bit lower. So this is also to be taken into account in the analysis. And well, this is an overview of the initial investment of the project. All the numbers are related to kilowatt peak. This is DC. So we can see that the modules are slightly more expensive, about the 20%, but this is changing with the time. We are expecting for the next years that the price of the modules get more like the tradition, like the south-oriented monofacial ones, but they are going to cost still a little bit more. About the inverters, they are sized smaller in our case because we don't have so much. We don't have as high peaks as the south-oriented system, so we have a little bit less there. The mounting system is indeed more expensive than the fixed systems, but this is also expect to get lower with the scale production. And the cabling is a little bit more expensive since the distance is bigger between the rows and the panels, so you need more cable. But we have seen in our projects that this difference is balanced with the lower cost of the inverter. So in the practical, it's more or less it's more or less the same. So watching the OPEX, the cost of operation and maintenance, we can see that the costs related to the lands are slightly higher in our system. This is because the system needs more space, so you need a bigger extension of surface. But on the other hand, we get lower land leases, because of course the owners of the land can still go on with their activities, so they have an extra benefit in it, and the land lease is lower indeed. And in maintenance it's more or less the same, so we put 0% there, and the other factors also remain the same. So when we get to put everything into the calculation of the levelized cost of energy, we get slightly better numbers for our system. So yes, it's not far away, but it's similar. We have to take into account, we have to remember that we have a slightly higher energy yield, and also apart from this, apart that we have a better levelized cost of energy, we have extra revenues from the market. So the fact that we generate electricity in the morning and in the evening allows us to get better prices for the same amount of electricity than what you get with south-oriented fixed systems. So we have seen this difference in our pilot plant in Losheim. The average is 3.5 euros per megawatt hour, and we are seeing a tendency in the market to increase this gap. So we are calculating 4% extra each year, and well, we are seeing that this tendency is not only in Germany, it is everywhere, because the growth of the PV share in the market is growing in an exponential rate in some markets, and worldwide it is like this, and the electricity demand is growing in a more linear shape. So the gap between you are starting to see more negative prices in some days because you have too much energy at noon and not in the evening. This is how also the business models of the batteries are working. So our profile has this extra revenue, and we are confident in saying that it is going to grow in the coming years in all markets, or almost all markets. So it is possible to make also in some cases, at least in Europe, I know that it's possible to simulate these extra revenues with some software. So this could also be an option for increasing the certainty in investments. So making a brief summary about what we have seen in this project, we have advantages in permitting that allows us to get surfaces that were out of scope before. We have a higher investment, and we have higher operating and maintenance cost. But on the other side, thanks to the higher energy yield in this case and the extra revenues of the market, the project gets better investment returns that would have been the case with south-oriented and fixed systems. So the second case that I wanted to show you is a business case. This hasn't been built in reality, but it is kind of a reflection of a case that I find very interesting. It is this example is about a PV plant, a south-oriented fixed PV plant with an installed capacity of 9.4 megawatt peak. The grid connection capacity is 8 megawatts. The built area is 12 hectares, but the land is 25 in total, so we have space. And the yearly specific energy production in this specific point is 1,209 kilowatt hour per kilowatt peak. So this is the exercise that I wanted to show here is what happens if in a moment you get more grid connection capacity than before. So what I wanted to analyze is what happened if the capacity grows to 12 megawatts in total, and I wanted to analyze what happens if you build more south-oriented PV, or if you install instead vertical bifacial PV. So what we're going to see is something that has been shown already by Sasha and Peter as well. So the idea here is the orange curve is the 8 megawatts of the 9.4 megawatts of south-oriented. The blue one would be the vertical bifacial extra capacity that is installed, and the gray one is the resulting curve that results from both systems. These curves are a mean of the year, so it is all the days counted together. And what I want to show you here is that if you had to, so in this latitude that we are analyzing, you have the same specific yield for both systems. So you don't have the advantage anymore that you had in Germany, where the latitude is high, but you would be, for example, let's say in Spain or in Italy or farther south, where we don't have an advantage in specific energy production. The result here would be that with our system, you are able to install 5 megawatts instead of 4.7 that you would be able to install with south-oriented. So you get 300 kilowatts hour more. 300 kilowatts. This is wrong. The slide is wrong. It is kilowatts more. And the other parameters are the same. So in this case, you would get a lower LCOE with our system, but a higher LCOE, so it would be more expensive, but still you would have the advantage of the market. So this is to show how the possibilities are wider than, like, LCOE is not the limit, but you also have the revenues. So it is possible to have beneficial numbers further south than you had in Germany, for example. So well, the other so having seen both the first two projects more in depth with the financial calculations and so on, I want to show you now some business cases and case studies that I also find interesting. And this is only like a first comment for maybe analyze interesting concrete projects in the future. So let's imagine that we have a planted surface of 3 hectares, and we need 100 kilowatts to pump water for irrigation in this case. If we do the maths with the basic thumb rules of our systems, you will get to see that with vertical bifacial PV, you only would need 142 square meters, and with the south-oriented system would be needing 1,000 square meters. In spite of that, you do need more total area, but since you can do agriculture in between, the overbuilding of the system is 5% instead of 70% that you would need with PV. So this is an interesting business case. Also, the profile, the generation profile that, as we have seen before, is more steady. You don't have high peaks, such as high peaks as monofacial south-oriented systems. This is also the case in the rest of the years. Like the difference between summer and winter isn't that big, so it is beneficial for dimensioning any kind of machine that depends on this energy system. And well, this is a dairy milk farm that was built in Ireland. This is a small project that is a pilot project that is being tested right now. What is interesting in this project is that they built electric fences in between of the rows, but it is important to clarify that this is not strictly needed. The system has been also tested with cows without the electric fence, and it has worked very well. And the product that has been used here was our solar fence. So basically, it's similar to the mounting system itself. It is ramped to the ground as well, but you have the variant of one module, one row, or two rows of modules, and it has been, as I told you before, it has been tested with livestock farming. If you see the picture of the right, you have the grass has been more wasted next to the panels. That means that the cows like the shadow. So this is also the case with some kind of crops. It's not strictly the case that the shadows are detrimental, but sometimes they can be beneficial depending on the climate and the type of agricultural activities. Also, at the left, you can see that the cabling is done inside of the structure, so no animals can generate any damage to the cables. And what is very interesting as well is that in dairy milk farms, you have a very similar energy consumption profile than our energy production. So they fit very well in this kind of applications. Well, and some key numbers of the solar fence in general for you to take into account when thinking about a project. These are this is the power per meter that you have to calculate for the fence. The energy yield, you can take into account that it can be slightly higher than the mounting system, because the mounting system in utility scale generates shadowing to itself. So this is not the case here. So you might have a slightly higher energy yield, and also depending on the different orientations, you can get different generation profiles. It is good to remember, as Peter told in the previous webinar, that the orientation of the fence is not significant in energy yield in the total amount. The maximum difference between the total energy yield between different orientation is of 3%. So there's no problem if you rotate them and so on. This is a chicken farm in Austria. You can see that the fence has in the lower part a net that doesn't allow the animals to escape. And you also see that what we're talking about previously in the other slide, that you have some fences that have different orientations. So the profile is not strictly east-west, like we have seen in the utility scale, but it is slightly different. These are more pictures. You see here the same. The grass is gone next to the panels. That means that the chicken like this kind of shadow. And well, apart from the ramming variation, we have some slightly different options for the mounting. Here we are seeing the concrete foundation. That would also be an option if ramming would be a problem. So it is drilled, it is filled with concrete, and the posts are then installed inside, and everything else is the same as in the other case. We also have wall mounting. This is more for residential or industrial applications, which can be very interesting as well. We have been analyzing some projects apart from the ones that you see here. These are also from our partner in Austria. And also we have the premium version of the fence. This means the profile is square instead of C-shaped, and it is also powder coating instead of galvanized, so it is aesthetically more beautiful. And well, if you want to have an overview of the models that we have developed so far, you can have them here as a summary. And well, we are seeing also very interesting opportunities here, not only in utility scale, but in more smaller projects in residential and industrial, as well as in farms. So, well, this was all about the presentation. I hope it was useful, that you enjoyed it, and well, we are here with Heiko Hildebrand, who is joining me here.